Have you ever wondered how animals can see depth with just a single eye? A lot of the animals do not have binocular vision like we do, which means that they do not have two eyes with overlapping fields of view to be able to discern depth, but they can remarkably still hunt and live in the world just using depth from a single eye. Moreover, in the recent times, we have seen these amazing self-driving cars being able to estimate depth from a single camera. So let's dive right in and learn today and discover and demystify how we can learn monocular depth. To set our problem statement, we want to learn depth from a single image. So in this particular case, we have a single input RGB image. It's red, green and blue channels here. But remember that it can also be a grayscale image. A lot of the animals do not perceive color like we do. So it can be a 2-channel image, a 3-channel image, or just a single channel grayscale image too, which is just the average intensity for each pixel. And we want to feed this into a magical deep learning model, which essentially gives us the depth of the scene at every single pixel. In this particular case, I'm visualizing the output, which is a single channel depth map, as a plasma color map so that it's easy for us to see what the depth is in the scene. So the question is, what is the secret recipe to a deep learning approach? What do we actually need to enable this thing to happen? The first thing is we need an input dataset. The input dataset needs to have a certain characteristics. The first thing is it should be clean. Second is it should model the distribution we want. And it should be varied enough in the distribution so that we can actually learn the characteristics of that distribution mapping. So the magical deep learning, we need to choose the architecture, which is dependent upon the output we want. We might want to choose to maximize the accuracy in this particular case, or we might choose to reduce the number of floating point operations or the number of operations because we have very limited computation power. Or we might decide that we have very limited memory or RAM on our computer and we need to reduce the memory footprint. Or it could be a weighted combination of all these things. Generally, that is what is the practical constraints, which is called SWAP or size, weight, area and power constraints. This is where the true embodiment nature of embodied intelligence comes from. And we need to also decide the output or the loss function, which means that we need to decide what kind of output do we want. Do we want a per pixel output? Do we want an average value output for the entire image, and what kind of things? We also need to decide, do we want the output or loss to be supervised, which means we have labels, we have ground truth values for the depth. Or is it unsupervised, which means that we do not have any labels and it needs to figure it out itself. Or is it self-supervised, wherein we have some constraints which actually help us get this depth in a very well manner. And is there any domain knowledge about this problem do we have which we can use to make this problem simpler to learn? So let's dive right in and let's start filling in each of these boxes so that we can formulate this problem once and for all. So we are going to say that our input dataset is made up of color images, RGB. Again, you can replace this with grayscale or a 2-channel image to mimic an animal eye. We want clean dataset. The question is, how do we get a clean dataset? So clean here means that the data is representative of what we want and the labels are actually good to go along with that dataset, right? So the cleanliness of the dataset could be about you scrubbing through the data and only utilizing the data which is right. And this is a laborious manual process, right? For the distribution we want and it to be varied enough, we will capture data from realistic world scenes, which models what we want because we want to put this robot in the real world where it is deployed in like a self-driving car scene or inside an indoor environment or things like that. We want to choose the realistic scene which we really care about and we want to be varied enough in that. For the architecture, we want the output to be a dense depth map, which is per pixel depth map. So the output resolution of the depth in the spatial dimension is exactly the same as the input RGB image. So for accuracy, flops and memory, let's not worry about that right now. We can always choose a better architecture later to make this happen, but let's start with something simple first. So for the kind of output, as we said, we need a dense depth map. For a supervised problem, we will just pick the simplest one, which assumes that we have labels, and we are going to pick the supervised problem. For the domain knowledge, we will say that I know nothing about computer vision. I am a machine learning researcher, so I am going to just do this as a machine learning problem right now and not worry too much about the computer vision aspects of it. So just to quickly recap, this is the input output. So we have input as an image, which is a natural realistic scene. In this case, it's a cowboy riding a horse and trying to like do a bullfight, right? And we want to get a per pixel depth map, and this is what it looks like. In this particular case, we have color coded this as hotter colors are closer and cooler colors are farther away. And this is the plasma color map. So the question is, how do we actually get this training data? In a simple world, we can basically say that we have a stereo camera with a known baseline B, and we go collect the data ourselves. If you have a bunch of grad students working with you, you can basically delegate them to do this. Or if you are in a company which has a lot of engineers and a data collection experts, you can tell them, okay, hey, go get me data, right? If you are a company which is already selling products, you can basically collect data from the fleet of your robots or vehicles which are already deployed, right? But in general, collecting data like that is really painful and really arduous and expensive. So we don't want to do that. So can we do better? The answer is yes, because we have a lot of 3D movies which have been made over the years. So what we want to do is we want to get data from 3D movies. But the first question is, how do we know the baseline for this 3D movie, right? The answer is not that simple, because like you cannot go and ask the person who took the video or who made this video, and if they're animated, like the baseline and the focal length are completely made up. For example, in this particular case, the movie The Planet of the Apes, the apes are like larger than life size. So the relative scale is still not correct, right? So it might be really hard for us to get data like that. So what can we do instead? Can we learn disparity, which is the matching between the two images, instead of depth? Do we really need depth? Where we say depth is telling us how far away something is in physical meter scale, like 1 meter, 2 meter, 3 meter, and so on, or like a foot or like a kilometer, right? Disparity is just saying, okay, like between the left and right image, it has moved by 5 pixels or 10 pixels or 20 pixels. So the answer is disparity is actually easier to learn because it's just a pixel to pixel mapping, and it's obtained by matching one image to the other. And the depth would not generalize because we do not know the focal length or the baseline, like I alluded to before. The question is, do we really need focal length or baseline for learning the disparity? The answer is surprisingly no, because disparity is just modeling the pixel displacements between the two images, and we can obtain this through matching, right? So to obtain this disparity D, you will use a very fancy classical matching algorithm, and it will take a lot of time for us to run on compute power, but it will give us really accurate results. The question is, going back to, how do we actually learn depth then? When did we get the metric depth here from? The answer is we don't. We just learn the scale depth instead, which means that we will learn the relative scale in every single image, which is that, okay, approximately monkeys are like half the size of the trees, and so on and so forth, right? And that's what we will learn here. So we got the data from 3D movies, but in the modern world, you can do even better, wherein we can generate these synthetic datasets with arbitrary textures and arbitrary like shapes in 3D, and they are floating around in space. So it really learns the geometry rather than just the implicit appearance of the data itself. This is called domain randomizations, and one such example of this dataset is called the Flying Things 3D dataset. So there have been a lot of datasets which have been produced from a similar ideology, and this is just a list of a few of the datasets which are common, and here are the number of images which go all the way from 3000 images to about 1.5 million images in some datasets. This is great. You can do a mixture of these datasets as well, which gives you more power and it gives you more variability, and that's what we will do. So just to recap, we choose our input dataset from 3D movies. And for the architecture, we are going to keep it simple. We are going to use the most common ones, which is a UNet or a ResNet. Remember that you can choose an architecture of your choice, and we will talk about a few in some time. And for the output or the loss, we are going to keep it super simple. We are going to just do a supervised L2 loss. Using this philosophy brings us to the first work we are going to discuss. This is going to be called Eigen et al. It's a very old paper. It's a 2014 paper about almost 12 years ago. And they do exactly the same thing we discussed, which is take in a RGB input image, in this case from the NYU V2 dataset, and you basically feed it through a bunch of convolution layers, and you basically get a coarse depth map, and you feed it through a bunch more convolution layers, and with some fancy architectural math, you basically get the refined depth map, which sort of resembles the depth map of the scene. In this particular case, the darker the color, the closer it is to the camera, the brighter the color, the farther away it is to the camera. Instead of doing a simple L2 difference, what they do is they actually implement the square of difference of the log. The reason they do that is because log helps you compress the range of the depth, and we perceive depth as close, the difference in depth as closer as things go far away, because it doesn't matter too much, because the percentage is very small in error when it goes far away, and that's what is mimicked here in depth. Generally, for robotics, also this is important, because the closer something is to you, the more accurate the depth needs to be, because you want to do obstacle avoidance. The farther away something gets from you, the depth accuracy does not really matter so much. Okay, beautiful. With a method like this is fairly simple. The problem that can happen is that it could overfit quite a lot to the dataset you train on. What I mean by that is, it will learn the relative sizes and scales based on appearance in the image. If you train it on a queen-sized bed and you suddenly show it a twin-sized bed, it might not work well at all, right? And that's the problem. So in other words, if you have the same cowboy scene from before, you can have the depth map like this, and maybe there is a shifted scale in the depth map, and the colors look a little different, or it could be a scaled depth map where everything is scaled up or scaled down, right? To give perspective, if our network predicts either the left one or any of the right two ones, ideally they should be equally accurate, but it is not captured in the Eigen et al. Paper, which we just discussed. So how do we fix this? This is exactly what the Intel MiDaS paper does, where they use a lot of data from the 3D movies dataset we just talked about. And again, remember that this is captured through a stereo camera. We don't have the baseline B. So our loss is supposed to be invariant to both scale and shift in the prediction of the depth output. That's what we just saw. So in other words, if you have depth of a single row, X here is just the row of the pixels and Z is the depth. The red one could be the ground truth, blue one could be the prediction. We know that the shape is matching, which means it is correct. And this is exactly what is represented in the scale and shift invariant loss. I would not dwell too much upon the math here, but this is what is being captured at a fundamental level here. And we also know that the depth cannot vary significantly over pixels, which means that the textures of the objects in the real world are smooth except at the object boundaries, and that is captured through the smoothness loss, which essentially says that I penalize for super high gradients of the changes in the depth values, and that's what we are doing here. The final loss is just a weighted combination of the scale and shift invariance loss and the smoothness loss. Just with this and a lot of data, Intel MiDaS does brilliantly well. And as you can see from the top row, the input varies, right? It's an outdoor scene where women are playing soccer, where like the person in the back is out of focus, to a completely indoor scene which everything is in sharp focus and it's a high dynamic range scene. And the depth map, which is the bottom row, works really well, right? And the beauty here is that this work actually does generalize fairly well to the real world. This work is from Ladin Colton's group, who was at Intel at that time, and now he is in Apple doing brilliant computer vision work as well. This is one of the first works which use the word zero shot in the title. So zero shot here means that you can train this on a giant data set, which they have already done. You can take the model and put it on any real data set which is different, and it should in theory work really well. it should generalize across datasets. And that's a beautiful thing for the robotics community and the vision community, because that is what we need. We need one model which works almost every single place, right? And that's the beauty. Building on the success of Intel MiDaS, basically the authors also replaced in the second version, which is MiDaS 2, they replaced the convolution neural network using a vision transformer, where the idea is that you have an image which is chunked up into smaller chunks, and each of them are embedded into an embedding space, and it's all fed into a transformer architecture, and it gives you much better results because the transformer architecture works with a lot more data and it's less biased compared to a convolution neural network. So when given more data, generally vision transformers perform better than the convolution neural net counterparts, and that's what we see here as well. Just as a side note, I'm going to also give a quick 30-second primer on what a vision transformer is. Stay tuned and subscribe to the channel for a detailed video of how a transformer works and why it is so nice compared to a convolution neural network, and why is it actually unbiased compared or less biased compared to a convolution neural network. The idea is that a vision transformer draws heavily from the language transformer, which is when you start typing into your chatbot like ChatGPT, it is essentially encoding each of these chunks into something called an embedding, which is essentially then transformed, and they are learning the relationship between these embedding spaces to be able to discern and understand what you're trying to say, right? A vision transformer does something similar through patches, wherein you take an image, you crop it up into patches like 8x8 or 32x32, and you feed this into a patch embedding layer, wherein like you have some set of convolution layers which essentially make this into a linear layer for you, and then you feed this into a transformer encoder, which is the gray box here. The transformer encoder essentially knows the mapping between these patches, which has to co-occur with what, and it associates a weight with it. And essentially what you see on the right side is the transformer encoder, which is fairly complicated, and this multi-attention head is essentially what brings all these patches and the probabilities of these patches being together, and it utilizes and harnesses the power of big data to know what the depth should be, right? With this beautiful architecture, MiDaS 2 does brilliantly well. As you will see here, the input images are varied, and you can see that with the DPT hybrid, which is in the bottom, in the middle and in the bottom, you see that the branches are fairly accurate, while everything else is being accurate in a high contrast scene as well. And taking this to the next level, again, these are all relative depths. Nothing is metric yet. We still want to learn metric depth for something like robotics, right? Because we want to say something is a meter away so that the robot has to do obstacle avoidance and things and so on. So Zoe depth essentially does what I call as cheating physics, which is taking a single image and trying to get depth from that. In theory, getting depth from a single image is almost impossible because you generally do not know some statistics of the scene. Given some good statistics of the scene, you are able to discern depth, which we have seen before through single view metrology, where vanishing points were used and so on. But when we are trying to do this with a neural network, it's much harder because it's really hard to model what kind of a scene we are looking at. And Zoe depth does this in a very creative way, wherein like they utilize and leverage a model like Intel MiDaS, which gives us relative depth, and they learn how that can be transformed into metric depth, which is basically predict relative depth first, which has no scale, and then you predict the scale which is appropriate to this relative depth, so you actually get the metric depth at the end of the day. So what Zoe depth gives us is zero-shot metric depth. This is in collaboration of Intel with KAUST, and it's a beautiful paper. I would highly urge you to read it. So the idea is that you have the same RGB image from before, and you basically have an encoder and a decoder block, and the decoder block basically produces what we call as metric bins module, and you basically feed this like predicted relative depth map, and you feed this into a bunch more convolution layers, which essentially gives you the metric depth, which is the right metric depth, right? And Zoe depth map predicts the metric depth. This uses a fancy binning scheme, which they have adapted from a paper called local bins. The idea is that you have an image and you have this green pixel and the blue pixel, So when you predict the metric depth, you want to basically bin how the relative depth are mapping to the metric depth in a completely different bin, right? So the idea is that instead of doing one binning scheme for the entire image, you would do a binning per pixel, right? In this particular case, you'll see that the green pixel bins are completely different than the blue pixel bins, and this is what gives you the high accuracy, right? As you come closer, you want bins to be closer to you because like that's super important. High resolution is important there. As you go really far away from the camera, you want bins which are spread more apart and maybe very farther away from you, and that's what we see here, right? Doing something like this actually gives us beautiful outputs, and you'll see that this is exactly what was used in the local bins paper to get really accurate depth maps. And using this fundamental ideology and combining it with a few more architectural tricks, our Zoe depth does this even better, right? Zoe depth, again, just to recap, adapts the same concept from local bins. They do the local binning and they basically feed it through a bunch of multi-layer perceptrons in different scales, and that is what gives them the final depth map, which is metric scale. So to recap, Zoe depth takes in an input as an RGB image, and if you compare the second column to the last two columns, you will see that we have very accurate results. Again, these are all in metric scale, right? This is the beauty here. Zoe depth works great, but the question is like, can we do even better than this, right? So we want to harness depth from the power of data, which is like the more varied amount of data we have, the better we will learn the skill of what actually maps to what, and we learn the relative sizes based on appearances. The question is, we can't get that much labeled data sets, right? And that's the problem. I mean, that's the whole point we started this with. We have a little bit of data which is like labeled like through stereo depth cameras or through like a 3D scene or a 3D movie and things like that. But we have a lot of monocular videos, which is a single camera video through something like YouTube or like movies and things like that. Like, how can we utilize the power of what we have learned from the stereo camera's depth model, and how can we utilize that to unlabeled images? That's what this depth anything model actually does. The idea is that we have a labeled image, which is RGB image with its corresponding depth, and we have a prediction for that. And we have an unlabeled image wherein we do not know the depth map, and we basically are predicting the depth for that also. And we want to learn the semantic mapping between these two. Just based on the semantic mapping, we are now able to obtain the depth map. Another way we could do this is also generate something called a pseudo label through something like structure from motion, which is a 3D reconstruction based on a monocular video. And so we can basically learn that and match that with the prediction which we are getting from the labeled image. And let's see how we do that. And this is a beautiful work from TikTok. The idea is that to obtain semantics, humans are really good at semantics, right? For example, in this particular image, if I ask you to point at the head part of the airplane and the head part of the bird and the head part of the elephant, we humans will point at the front of the airplane or the nose, and maybe the beak and the head of the bird, and maybe the trunk and the head of the elephant, right? And we all almost agree upon an equivalent definition of what the head in quote unquote looks like, and that is the semantics here, right? So this is exactly what we are trying to do for the semantic preservation module. This is an output from a paper called Dino V2, which is from Meta. And the idea is that we want to utilize this like a large foundational model which has learned this mapping, and we want to enforce the same set of constraints at the feature space for a depth model. So the idea is that you predict the feature space from a Dino V2 for an image of your choice, like we were talking about for the unlabeled image. And what we want to do is we want to take the depth model features, which is like you take the same image, you pass it through the depth model we were just talking about, it gives us features, and you take the features from Dino V2 and you say that these two features have to be similar, and that is the semantic preservation we were talking about before. And that's what goes in there. And doing this and combining this with pseudo labels from LiDAR matching or structure from motion and so on and so forth, we train this with a lot of data because we can have some amount of labeled data and a lot of unlabeled data. This works really well. And just to recap, the semantic preservation happens through a feature alignment loss, which we just saw. This is great. And when you actually train this and you compare this to MiDaS v3, we saw v2, there is a MiDaS v3, which is an even better version. We see that the depth predictions are super accurate, especially for thin obstacles, really harsh lighting conditions, for blown out areas like this white area, and even like super dark areas. You see that the prediction of this model is way better than the MiDaS v3 model. So the keen viewers might be thinking, isn't depth just an image translation model? Why is this so hard? Why is zero-shot monocular depth so hard? Can we not just take an RGB image, transform that into a depth image? Can we not just learn this transformation mapping rather than trying to really predict what it is? Do we really care about it? Can we not hallucinate this? Can we not generate this? The answer is kind of yes, and that's the question a lot of these people have asked, right? For example, the domain can be different, which is indoor versus outdoor. The field of view of the camera could change. The camera properties could change. The lens properties could change. And it's really hard for a depth model to adapt to all these changes, right? Would it not be just better that we hallucinate or generate depth? We have a lot of these beautiful models which can actually do generative modeling or generative AI, as we call it. Can we not adapt the same ideology what ChatGPT uses to hallucinate new things? Can we not do that for depth? That's the question here, right? Stay tuned and subscribe to the channel for a detailed video on diffusion models, which will come later in the future. For now, let's just go with this, right? The answer is yes. And this is one of the questions like researchers from Google and DeepMind have asked. There is this paper called DMD, which is essentially utilizing a diffusion model to generate depth from an input image, right? So as you see, compared to the Zoe depth, which gives us metric depth we saw before, the DMD model, which is the diffusion-based model, gives us metric depth even more accurately compared to the ground truth. Compare the second column to the last column, and that compare the last column to the last but one column, right? You see that the accurate results are way more accurate. This works really well because diffusion models can harness the power of data even better than simple classical transformer-like modules, right? Okay, this is great. Can we take this one step further? So this paper basically uses something called as intrinsic LORA. Basically, we are trying to do image-to-image translation. And like the idea is that you take the image and you try to predict the normals, the depth map, the albedo, and the shading. And when you learn all these things together, we can do really well. And this is not even using a really fancy model. This even works well with a simple model like GAN. But with diffusion, like Stable Diffusion 2.1, you see that the results are way more accurate, right? And it just works much nicer. And this is a work from Toyota Institute of Technology, Chicago, and Adobe. TTIC is very famous and has done a lot of influential works. One of them being the Kitty Benchmark Vision Suite, which is one of the biggest benchmarks for SLAM systems, which is the earliest SLAM vision benchmark. That was a collaboration between Karlsruhe Institute of Technology, KIT, from Greece, and TTIC, which we just saw. And this is a beautiful work, and these models are all available in different versions of Photoshop now, and you can utilize them. So there is another paper which uses a similar concept. The idea is that you want to capture the extensive prior which these diffusion models like large scale foundational diffusion models like Stable Diffusion have to generate depth from a single monocular image. So we start from a pre-trained Stable Diffusion. You encode the depth image X and the depth image D into a latent space using the Stable Diffusion variational autoencoder. Then you just fine tune the UNet, which is basically predicting the output depth map by optimizing the standard diffusion objective relative to the depth latent code. Image conditioning here is achieved by concatenating the two latent vectors from the depth map image D and the input RGB image X and feeding them into the UNet. The first layer of the UNet is modified to accept concatenate latent code, and just using a simple standard diffusion objective, you train this entire model, and this works spectacularly well. It's a very simple idea, but it works really well. And it's using the frozen Stable Diffusion model to be able to train a simple, smaller depth estimation model, but utilizing and harnessing the power of data which has been embedded into the Stable Diffusion, right? And that's the whole trick here. We want to utilize a lot of the learnings from a lot of data, but we don't want our depth model to be really heavy and bog down the entire system. That's the trick here. And clearly you can see that when compared to MiDaS or DPT, which is the model from MiDaS v3, we can see that the Marigold produces much sharper depth for thinner objects. It works better with harsher scenes. It works better with really small objects, and the depth values are just much crisper. So the problem with all the models we have seen before is that they operate on single images. When you're trying to put these on a robot with real embodied intelligence, you want consistency in the depth maps over time. For example, we fixed the zero shot issue with a lot more data, but the problem is we never enforce the fact that if it is continuously running in a video or frame sequence, the depth has to be consistent and the scale has to be consistent. And that's a really big challenge, because if you're trying to spend a lot more energy trying to figure out what the scale is, what's the point? What's the point of even predicting depth map? And just by training a depth model like we saw before, the consistency is not that great. If there is a sudden car which comes in front of you, the depth map can go haywire because the entire depth scale shifted, or if something like a light flickers at the end, the depth map can go crazy as well. So this paper called DepthCrafer basically does something really clever, which is it uses a conditional diffusion model to get depth over a sequence of input images or a video, right? The model is essentially trained in 3 stages. In the first stage, wherein the temporal and the spatial layers are progressively learned based on compiled realistic and synthetic datasets of different lengths of time, right? During inference, an open world video, it's any random video, it can generate temporally consistent long depth sequences with super good details. And the whole idea is that this entire video is initialized from Gaussian noise, because remember that it's a diffusion model and it does not require any supplementary information like camera poses or optical flow, and it's all implicitly learned the modeling of depth. So the 3 stages are basically, they train it by first learning both the spatial and temporal layers, then they freeze the spatial layer and only learn the temporal layer, and then they swap the 2 and so on and so forth. And they really do an amazing job at modeling this both from an engineering perspective and a scientific perspective. And as you see here, you can clearly see that for a video which is as complicated as the horse jumping, the camera moving, and there is these fine brushes of the hair of the tail of the horse, you see that the video is the output depth is actually really consistent in the last row. And you see in the middle that the depth anything v2 is not giving you consistent results. Remember, we saw depth anything. This is the second version of the same depth anything model which we just saw. And this work is from Tencent AI Lab, and it's a beautiful work and it works really, really well. So here is another comparison of DepthCrafer, which is this paper we are talking about. You see the temporal consistency here to be much better, which is no flicker compared to chrono depth or depth anything v2 or NDVS. So the question now is monocular vision solved? We have given enough compute, we have given enough data. The compute here is used for a lot of these fancy diffusion models which we saw at the end, and data is used for all these transformer based modules or even these diffusion modules which are very data hungry. Is monocular vision solved? Is it enough? Have we conquered this dream of just being able to predict amazing depth from a single image? So let's take an example of the state-of-the-art monocular approaches we have seen before, right? This is an image in one of our experiments where we are flying one of the aerial robots towards another aerial robot, and the goal for the view, the aerial robot where the view is seen from, is to dodge the other robot coming towards us. When you predict the depth map of this, it's really hard for us to see where the aerial robot is. More interestingly, it's important for us to zoom in on this person, right? You can clearly see that half of this person is at a different depth, which means that the torso is detached from the lower body, and the other half of the body is really far away, and the top part of the body is really close to the camera. Does this really make any sense? Should we all start wearing things like this because we don't want to be hit by a self-driving car? That really doesn't make sense. First, let's ask the question, why is this even happening? What happens in life in general is that we have a lot of scenarios that can occur, but we don't have enough data for all the scenarios of occurrences. When people collect data, what in general happens is it is a long-tailed distribution, something like this, wherein you have a lot of data in like really good scenes like this, like driving in sunlight, like in California, or flying in a forest with like beautiful sunlight. You have a little bit more, you have a lot lesser, but like substantial amount of occurrences in like harsh driving conditions like snow. But you have very little data in things like a road accident, things like a forest fire, and so on. And there are a lot of these scenarios, which brings us to the long tail of this distribution, which makes it really, really hard when you want to generalize across scenes, right? So let's look at a few cases why collecting data for these kind of things is really hard. One is it could be like things could be implausible, like having an aircraft on a road. It could be really expensive because you might have to crash a few vehicles to get data for like accidents. It actually could be disruptive for us to like put fire to a forest just to collect data. Or it could be really arduous to collect data in something like an underwater scene because it's really, really hard, right? So you might be wondering, hey, this can never happen. Why are you showing us this kind of stuff, right? So when an emergency flight has to land, if it cannot find a runway or a patch of grass, the pilots are trained to land on a freeway. So this indeed can happen. And very rarely, there could be a tire blowout, which could happen from a car and hit another car, and the other car could go flying. Forest fires are fairly common in California, so you could see a scene like this. And maybe you have an underwater robot which is trying to detect something like oysters, right? And that could happen as well. So let's feed in one of our like standard MiDaS models, which is one of the state-of-the-art models, and let's see what the depth model is. And this is the MiDaS V3, which is the transformer-based module, right? You'll see that the depth map for the airplane is really bad because it has never seen something like this before and it does not expect this, right? The airplane has basically blended into the road and you cannot clearly identify that there's an obstacle there, right? And in this particular case, the car looks much closer than it actually is, which could make it really hazardous to take a dodging maneuver, which is not safe. And for the forest fire, you don't even see the trees anymore, though they are existing there because of the fire and the lighting conditions it has never seen before. It does not know what's happening. And in this particular case, it does not see the robot at all because it's never seen a scenario like this. Maybe you're wondering, hey, these are scenarios which are really hard and they're really rare. Why do we bother about this stuff? Okay, let me show you a simpler thing. If you've seen these like Looney Tunes shows wherein like the roadrunner basically does paint a road for the coyote to crash into. So let's see, we taken an image. This is from Amazon. It's a listing for a road image of a poster. And as a human being, even with just a single eye, you can clearly say that this is a fake picture, right? It's very evident because it's photoshopped in a really bad manner. And if we feed this into a depth map, it should ideally be able to say that, hey, this is a painting and everything around it is a wall, and you should be able to get the depth map. Guess what? It also predicts the depth of the scene inside. And this is really scary because if you were driving towards a wall with a painting like this, like a mural on the side of the road, it would think that there is a road on that mural, and the self-driving car might actually try to drive there. And that's the scary part here, right? What about glass buildings? We are surrounded by beautiful looking glass buildings, and glass buildings have been the Achilles heel of computer vision algorithms for all along, right? It's really hard. As a human being, you can see this glass building. I have included the boundaries. You know that this is a glass building and you know where the boundaries are, and you can fill in the depth based on the reflections and stuff like that, right? This is not a really hard image in that perspective. If you feed this into our state-of-the-art beautiful depth model, you'll see that the glass building on the right-hand side does not exist at all, right? And that is really scary. What about the same person photoshopped in different focal lengths? Can we actually do this? So it kind of works, but the problem is, like, if you see in between the legs of the person, the depth map is really bad, and this is very, very concerning. So essentially, most of these depth-based models like MiDaS work by learning patterns and the relation between these patterns and the co-occurrence between these patterns. For a transformer module, it works in an even fancier way by learning the co-occurrence of patches, but at the end of the day, they're all learning how something visually looks and how big that should be relative to each other. They're implicitly not learning physics, just like we do with a stereo camera. So whenever these patterns break, it could be through an illusion or something which is not the ordinary, through illusions, through reflections, through weird environments, these networks will confidently assign depth to the hallucination they have in their head, right? And that is a cause for concern, which we should be really careful about when we try to utilize and deploy these models into the real world through some embodied models, right? We really need to take into account what the robot can encounter and what is physically plausible and how the physics of it can actually interact with the real world to be able to do this well. And as researchers and engineers, it's our duty to really keep these constraints in mind when we design models for embodied on robots. So just to quickly recap, how do you get data for training a deep network based depth estimator? How does a monocular depth model work? And how does it even discern how far something is? What are the careful considerations needed for the depth loss functions which work well? And when does a monocular depth model fail? What can we do to improve the generalization performance of a monocular depth model? In the next video, we will actually talk a lot more about how we can do the last one. How do we improve the generalization performance of a depth model by introducing more physics cues so that it doesn't merely just learn the patterns which through the appearance, and it can actually learn and understand the physics of the model itself. See you next time. Take care. Bye-bye.